So I'm going to try to draw what this would look like as just the region in the xy plane. And so, again, x is allowed to be somewhere between 0 and pi over 4. And then y is going to be somewhere between 0 and tangent x. I know the tangent function crosses through the origin like that, and then it goes up really rapidly. What is tangent of pi over 4?
1.
Yeah, that would be 1. So when y is equal to 1 and x is equal to pi over 4, this tangent curve is going to intersect like right there. And so, yeah, the minimum y value is 0. And so this is kind of what the region looks like. And so we're saying, what is the surface area of this surface where the height is a function of only x above this region? And so we're going to use that double integral formula for surface area. So we take the double integral over the region, and then we actually take the square root of 1 plus partial z with respect to x squared plus partial z with respect to y squared dA. And then what would be partial z with respect to x? Yeah, that's going to be 1 over secant x, and then times the derivative of the inside function, and the derivative of secant is secant tangent, yeah. So in the numerator, I would put secant x tangent x, and so then those are going to cancel out, and I guess the partial with respect to x is tangent. And so then if I want it squared, then this would be tangent squared x. Okay, then obviously the partial with respect to y is what? 0. So if I square it, it's still 0. So back down here to my double integral formula. We'll take a double integral of square root of 1 plus tangent squared x. And the order of integration I'm going to choose is going to be dy dx. And I say that because I want x to be my outside integral, because that way I can go ahead and just use these constants for my bounds, 0 and pi over 4. Remember, only the outside integral, you're guaranteed to be able to use just constant numbers for your bounds every time. And then for my inside integral, it's okay if my bounds are a function of x. And so for my inside integral, I can use the bounds 0 and tangent x. Okay. So if I solve this problem, this integral, then we can get our solution. And now the trick is, what would be a good antiderivative for 1 plus tangent squared?
Is that for secant squared, or is it 1 tangent squared minus 1?
Yeah, I think you're on a good track here. So what I remember is that sine squared plus cosine squared is equal to 1. That's what we call the Pythagorean identity. But if I divide everything by cosine, then sine divided by, cosine squared. If we divide everything by cosine squared, sine squared of cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. Cool. So then where I have 1 plus tangent squared, that's just secant squared. And then the square root of secant squared is just secant. So
What was the derivative for secant? I forgot.
It's actually easy, so
Is it natural?
like the integral.
oh yeah, and then we're not even taking the antiderivative with respect to x yet.
Yeah.
We're taking the antiderivative with respect to y. So x is like a constant right now,
Yeah.
and that means secant x is like a constant right now, and that means all I have to do is multiply by y to get my antiderivative. And I'll evaluate that at 0 and tangent x. And so if I plug in 0 for y, then nothing important happens. But if I plug in tangent x for y, then I get the single integral from 0 to pi over 4 of secant x tangent x with respect to x. What is that antiderivative? We've already said it. Yeah, that's just the secant. And we evaluate at pi over 4 and at 0. And so remember, secant is the same thing as 1 over cosine. And so cosine of 0 is 1. But then what is cosine of pi over 4?
Also,
Yeah. Here we go.